So if you don't know how to create your own nodes on Godot, go watch the other video that I made explaining this. And here I created this class called Standard Camera 3D, which inherits from Camera 3D. And I'm defining this function here, which is declared on the node class, which allows you to capture inputs. And there's different types of functions that you can use to capture inputs. I'm choosing this one because of the hierarchy they have here. So this one triggers after the input event, which allows you to set up other events and stop the camera events from working. So if you have GUI elements, for example, it allows you to trigger the events on the GUI element and not trigger them on the camera, so the camera stops moving. And that's basically the function you have to declare to create the events. And then I'm just going to show the code, and then I'm going to explain the parts later. So basically you cast the event type here. This is the type you use for checking whether or not the mouse was pressed. So here it checks to see if the event is valid, and you do the switch statement here to see what kind of mouse event it was. So this one is when you have a right, when you have a left click. Then here I'm getting the position of the mouse, and I'm shooting a ray basically, which is a vector, to see if the vector is going to collide with anything. So from the camera position you shoot a ray, and then you check to see if you collided with anything, and if you did, that means you had a collision, which means you had an object. So you get this far here is going to be the far plane of the camera. Then you have the from and the direction, which is a normalized vector with the direction of the ray. And this function here, it comes from the physics server 3D, which is the class that Godot uses to keep track of the states of the physics simulation. So you can basically use this function here to get the space from Godot, and then you can use this result here, this data structure, and these parameters to call this intersect ray function, which is going to do the intersection for you. And if this is true, then that means that there was a collision. So I'm saving the object, which is a collision object 3D. It has to be a collision object 3D because that's how they designed the physics server. And this code here I just got from their implementation, and I just put on my class. So it's basically the way that they check on the standard event that they have, which is input event on the collision object 3D function, is how they check for collisions as well. So I'm basically doing the same thing that they do. So basically on the collision object 3D, that's the function that gets called. The reason why I'm doing the way that I did here is because of the order here, because I wanted to stop other camera events. So if you do it with the input event call, then the event's going to be triggered at the end here. It's not going to allow you to stop the camera moving. So that's the reason why I'm doing this from the camera class. But you can also do it on the object that you want to pick as well. You just change the way that you save the variables and that you move the object through space. So basically I'm holding a pointer to the object on the camera class if there was a collision, or it's going to be no pointer if there wasn't. And then a set of flag variable to determine that whether or not it was dragged. And then here's just the else to set the flag to when the mouse stopped being pressed. So it's basically mouse down and mouse up from the browser. It's just a flag to determine when to move the mouse. Then what you have to do is on the notification physics process, which is equivalent to the underscore physics process on the GD script function, is basically this spot here. You are going to check to see if there is the current object, which is the object that was intersected, and if the node is dragging, and then you call this function here, and that's the function that is going to calculate the movement according to the mouse movement. So it's basically the same calculation as before, and then you get the global transform from the object, you get the global transform from the camera, and here you're calculating the distance from the camera to the object, basically. And then you multiply this by the direction of the vector that has the ray, which is basically encoding the position of the mouse in three-dimensional space. This gives you the new position, which is going to be the origin of the transform on the object, and then you just call set global transform on the object, and that does the movement. So I'm going to explain how the camera functions work here and what is going on with SkyDraw, but let me show first how it works here. So you can basically see that it allows you to just pick the object and move around. So the reason why this works is that when you have a perspective projection, this function here is going to return the origin of the camera, which is a relative reference frame from the global coordinates. It's basically this representation here. So whatever you're seeing on the game or application you're building on 3 dimensions is going to be the near plane of the camera, which would be this rectangle here, and the mouse position is located on this rectangle. So the origin is the place you're shooting the ray from, which is going to be the 0, 0, 0 coordinates from the camera on the middle of the near plane here. And then they both take the mouse position as well, and this one is going to calculate what happens when you by passing the mouse position. It calculates the direction of the vector if the mouse was projected in 3 dimensions in relationship to the camera. So it would be as if it is projecting this mouse position direction here into the three-dimensional space of the scene. And the reason why I have to do this is because if you move the object with the position of the mouse straight up, then the mouse is going to move in 2 dimensions and the object is moving in 3 dimensions. So it's going to be off. So, but in this initial step here, what happens is that it returns actually the unit vector. So it's just returning the direction that the mouse would be pointing at from the camera in 3-dimensional space. And that's the reason why you have to get the far plane here in this first part and you multiply by the direction here, because what you're basically doing is increasing the length of the unit vector so that it reaches the end of the camera. And the calculation, which I'm not going to explain now because I also haven't spent much time studying, but Godot has another data structure called BVH, which is bounding volume hierarchy, which is basically a tree data structure that defines this 3-dimensional space with the tree. And this allows them to do collision detection. So they're basically using that data structure under the hood here to get the state of the simulation, of the physics simulation, and then they call this function to see if there was any intersection from this ray that goes from the origin of the camera to the far plane in the direction that the mouse would be at, is pointing at in 3-dimensional space. So if there was a collision, then the flag is set, and then you save the object. And when you move the mouse, it's very similar. It's basically the same calculation, but then the only difference is going to be that instead of the depth has to be adjusted so that instead of the ray going to the end of the camera, which would be the far plane, you're just getting the distance from the global coordinates, the global position of the camera to the position of the object, which would be the length here. So you're basically adjusting the depth, and this allows you to accurately move the object as if the mouse is projected on 3 dimensions. So it does the dragging. Then once you let go of the mouse, the flag sets to false again and it stops moving. So that's pretty much all you have to do.